Hello, everyone. Good evening and welcome to today's mathematical physics seminar. And hearty welcome to Sam, Professor Joseph Samuel, our speaker today. Sam did his master's from IIT Kanpur and PhD at IISc under Professor Mukunda, working on constraint systems. Since 1982, he has been at Raman Research Institute, currently as emeritus professor, and he is also the Simons visiting professor at ICTS. His interests are basically in geometry and topological aspects of physics, and he also likes to make contact with experiments wherever possible. His interests also include geometric phase, general relativity, soft condensed matter, and use of analogies in physics. He is also deeply involved in outreach activities. He visits schools and colleges, giving popular lectures. So today he will talk about a very interesting topic, why astronomers need to understand holonomy or Wilson loops. Over to you, Sam.
Thank you, Rukmini. Well, let me start my clock. Yeah, I'd like to thank the organizers, including Ashwin, Rukmini, and Pranav, for this invitation to talk in this forum. And also I'd like to thank Rukmini for the introduction. Let me now share screen and start the talk. Yeah, the title of my talk is slightly changed. It's why astronomers need to understand Wilson loops and holonomy. I left out the radio part because most of what I'm going to say also applies to optical astronomers with a few minor changes. So in the title, you can see the bilingual nature of the talk. The same object, which is called a Wilson loop in the physics community, is also called a holonomy in the mathematics community. It's the same object called by different names. So I'm trying to address both parts of this audience, the mathematical end as well as the physical end. This is work done in collaboration with Nityananda Tyagarajan, who is presently at CSIRO in Australia. He was earlier at the National Radioastronomy Center in New Mexico, USA, a little place called Socorro, where there's a large telescope of which you'll see a picture soon. And my other collaborator is Rajaram Nityananda, who was till recently at Azim Premji University. The work I'm talking about appeared in two papers, a PRL and a PRD in the last month. I'll be mainly talking about the first paper, because that's the part that has got more mathematical content. The other one is more experimental. And between the two of them, they cover quite a range suggested by the nature of the collaboration, because Nitya is a very hardcore radio astronomer, and Rajaram is somewhere in between the mathematics and the astronomy. And actually, he's all over the place. So this is a picture of the experiment, in a sense. This is a picture of the telescopes which are there in New Mexico. This is a large facility containing about 27 telescopes, all of which can be trained on the same object in the sky. Each telescope has a diameter of about 25 meters. And these people do observations to which our mathematics is applicable. So you need to understand the astronomical context in order to motivate this work. But once it's been motivated, I'll get on with the mathematical aspects of it. This is a picture of the very large array, the National Radioastronomy Observatory in New Mexico. And actually, the whole telescope is on a flat prehistoric bed of a lake. The plan of the talk is that I'll give you an introduction and then pose the problem and motivate it from the astronomical context. And then after a few counting arguments, I'll construct invariants in the next section, and then talk about non-unitary gauge groups and a solution to the problem that we started out with. And finally, a conclusion. Now, regarding questions, I've split up the talk into 6 or 7 sections. And after each section, I'll pause for questions. And if you have questions that can keep till the end of the talk, you can withhold them till the end. But if you can ask them before that during the pauses between sections, that will solve the problem of crosstalk when we try to talk through each other. So here's the introduction coming up. We'll start with single dish observations. So let's take a look at this picture again. This object over here is a single dish. Of course, it's working in concert with a large number of other dishes. But if you take this dish by itself, it has a diameter and it has an observing frequency, which I call mu. And I don't know if you can see the stuff behind. It's not visible on my screen, but I guess you can see it. The speed of light is given by wavelength times the frequency. And once you fix the frequency, the observing frequency, you know the wavelength of the radiation, which is being used to observe the sky. An important notion is the beam of a telescope. And that's basically asking from what directions is the telescope receiving energy or information. If you point a telescope at a certain region of the sky, you don't get a single point, you get a small spread around it. And that spread is given by lambda over d, where lambda is the observing wavelength and d, the diameter of the telescope. This is called the diffraction limit, and it serves as something like a pixel in the sky. It's an angular region in the sky, which you cannot resolve. If there are 2 stars closer in the sky than this angle, you cannot tell them apart. You can also think of the beam in a different way by using time reversal. Instead of looking at the telescope as a receiver of radiation, you can think of it as an emitter. And then when you put in a signal, electrical signal, what you see in the sky is a tiny spot, which is of roughly this size, lambda by d. To increase the resolving power, you need to decrease lambda over d. And actually, you can't do much with the wavelength because that is fixed by the fact that we have an atmosphere to contend with. And not all frequencies come through the atmosphere so cleanly. So the lambda is kind of fixed. But what you can do is to increase the size of the dish. So if you increase it, you get more and more radiation collected from the sky in terms of energy, but you also get more resolving power. And you can see tinier and tinier objects in the sky. Now, there's a limit to how big you can make the dishes. There was a dish in the crater of a volcano that was in Puerto Rico. And unfortunately, that crashed. That was about 300 meters in diameter. Right now, the biggest telescope in the world is China. It's 500 meters in diameter. And well, you can't make it much bigger than that because of human limitations. But you can do something else. You can take 2 telescopes and combine the signals from them. This is called an interferometer. Take 2 separated telescopes. The separation between the telescopes is called a baseline. And in emission, this is basically a glorified version of the double-slit experiment. If you put in a signal, which is correlated in amplitude and phase between the 2 telescopes, what you find is a pattern on the sky, which is like a sine wave. it's an interference pattern between the two telescopes. I'm treating the sky as a screen here. When you think about it in reverse, when you're absorbing radiation from the sky, what it does is to measure a particular Fourier component of the brightness distribution in the sky. So you have a function B of x and y, which is the brightness distribution of the source you're trying to observe. And you can go to its Fourier partner, which is p twiddle of u and v, where u and v are the conjugate variables to x and y. For a localized source, we can pretend that the sky is flat. And so we take an ordinary Fourier transform and not something involving the spherical harmonics. And then once you know the Fourier transform, p twiddle as a function of u and v, if you measure a large number of baselines, you can invert the Fourier transform and reconstruct the nature of the brightness distribution in the sky. So this is a big example of a picture which you can see after all this is done. We suppose that all the baselines are independent. That is to say, if I put 4 telescopes at the corners of a square, the parallel baselines are not really independent. They're measuring the same u and v. And the diagonals are independent. That way you should try to avoid redundancy. You get a lot of independent information if you use different baselines and put all this information together. This is called aperture synthesis, a very successful technique. And it has been responsible for observations of active galactic nuclei, which are energetic sources in the sky, quasars, and this led to the evidence for black holes. This technique is called very long baseline interferometry, when the baselines are about the size of the radius of the Earth.
Hi, Sam, can I ask something? Is this Fourier transform obtained when we superimpose the image from the two telescopes?
Yes, yes. You correlate the images. You correlate the signals received at the two telescopes, and that gives you a complex number. And that complex number is the Fourier coefficient.
I see. Okay. Thanks.
Yeah, and this technique is so sensitive that it can even measure continental drift if the two telescopes are in different continents. And certainly it can measure earthquakes if the earthquake happens while you're looking at a steady source. So this is the point at which I'll pause for questions, in case there are any. So if not, let me go on. Now I'm going to pose the problem. Suppose I've got n telescopes at different sites on the planet. The electronics at each site is different. The ionosphere can also be different. And if you're working in the optical regime, it would be the atmosphere which is different and which affects the observations. So what you get is a local corruption of the signal. The corruption of the signal at each telescope is independent of what happens to the other telescope. So this is a corruption, and it spoils the signal that we're trying to observe. We are in search of good observables, those that are not corrupted by local effects. Most observations to date measure a single polarization component, though there are a few observations beginning which measure the polarized component as well. We'll refer to this single polarization case as the scalar case because there's only one complex number to deal with. The distortion can affect the amplitude and phase of the measured signal and give you something which is dependent on local conditions at each telescope, rather than conditions in the sky, the astronomical source, which you are interested in understanding. So this is a new field now. It's called polarized interferometry. I think the first paper on this topic, there might have been others before. The first theoretical paper was by Broderick and Pescher. It applied in AppJ, volume 904, quite recently. Polarized interferometry can tell us about the magnetic field structure of the source. This is important for black holes and accretion disks, which are supposed to be dominated by magnetic fields. So polarized interferometry is what I call the vector case. In this case, you measure two linear polarizations coming from each telescope. And then when you correlate them, you get a 2x2 matrix. The distortion can be any linear transformation of the incoming electric field. So good observables are called closure invariants. So we have some questions about closure invariants. Firstly, how many are there? That's the most elementary question you can ask. These are the uncorrupted observations. That is, you make a lot of measurements, but from the measurements you form combinations which you believe are uncorrupted. How many of those are there? Secondly, can we find a complete and independent set and hand it to the astronomers for them to use in reconstructing the image? For some reason, my screen seems to have got stuck. Okay. Yeah. So the recent observations of the black hole in M87 actually use this technique in order to image the accretion disk of a black hole. So some of the observations involve polarized observations, polarized measurements of the object. So this needed Earth-sized telescopes because you need a large baseline to resolve this object, which is a tiny thing sitting in the galaxy M87. So what you need is a resolution of micro arcseconds in order to look at this object and image it. So this is going to inform our understanding of black holes, accretion disks, and of course, fundamental physics as well. Let's pose the problem more quantitatively. I have an interferometer with n elements labeled by A, where A goes from 1 up to n. The uncorrupted signal is EAP, where A is the telescope label and P is the polarization label. There are two polarizations. So what I would like to measure is SAB, which is the correlation between telescope A and telescope B. Each of these is a vector. And when I take the average value, the correlation between the two, what I get is a 2x2 matrix for each pair of telescopes. So on the other hand, the local corruption matrix can be written as GA, where A refers to the location of refers to each telescope. So the voltage at each telescope that is measured is equal to some linear transformation of the actual 2x2, the vector, the two component vector. There's no sum on A over here.
I have a question.
Yes.
Why are you calling the uncorrupted signal the average over the signals? Because I would have thought that the average corrupted the signal. Averaging corrupted the signal in some way.
Yeah, see, the signal, the averaging is basically measuring a cross correlation. And when you average it, you average out the noise. So you're measuring E of t, EA of t, EP of t, integral over t and divided by 1 over t. So that improves the signal to noise. And when you do that, the integration time is about 1 second. And in that 1 second, this matrix G might act on the signal and give you a corrupted version.
What is the matrix G?
Yeah, G is a 2x2 matrix. It represents all the effects which are corrupting the local observation. Because if you had a single telescope, it would just be a complex number. In the case of, if you had a single polarization, it would just be a complex number. The phase of this complex number represents the change in refractive index of the atmosphere. The amplitude will reflect the amplitude, the amplifiers acting up and not being quite constant. I think my screen is stuck. Let me just try to get out of this. Okay, it's unstuck again. Yeah, is that clear?
Yeah, I think it will be clearer as you go along.
Okay. So the measured correlation is actually measuring the correlation between VA and VB. And if you chase it down, you find it's basically the true structure of the source, which I call SAB, with GA acting on the left and GB dagger acting on the right. This is the way the corruption acts on the source structure coefficient. And what you actually measure is CAB. So G's and C's are both 2 by 2 matrices, and these are generically invertible matrices. So they belong to the group GL2C. And of course, it's elementary to check that if I take CAB dagger, that's the same as CBA. An important quantity is the autocorrelation, taking the observation of a single telescope and correlating it with itself. In that case, A dagger is equal to A. And what we find is that this is going to be Hermitian and a positive quantity by just looking at the quantity that you're correlating. Now, these quantities, because they are positive and positive definite, they're generally noisy because the amplifier noise generally causes the signal to vary wildly. And astronomers, although they measure this quantity, don't generally publish these results because of the noise on them. From the corrupted measured signal, we wish to construct quantities which are uncorrupted. So let me repeat the questions of interest. How many are there? Can we find a complete and independent set? Autocorrelations are noisy. Can we do without them? So again, I'll pause for questions.
Yeah, I had a question.
Yes.
So why do these G's have to be invertible in general?
Yeah, actually, generically, the G's have to be invertible because if they're not invertible, your experiment is flawed. You're not really measuring both components of the polarization. You seem to be responding only to one of them. The C's, on the other hand, could be zero, could vanish. Some Fourier components in the sky could vanish. And that does not generically happen. That most of the time, the Fourier coefficients will be non-zero. That's a good question.
And one more thing is that, so we see that what we measure is, so in your previous slide, we had that what we measure was GA, SAB, GB dagger, right? So, and these GAs are what are these corruption matrices. So it could be that, so are these corruption matrices defined by taking a product of different corruption matrices depending on how many of those act on a time interval? So are these defined for a time interval, or how are these defined, these corruption matrices?
No, they're outside the time integral. The integration time is just about 1 second. And in that 1 second, these objects don't change very much. Like the ionosphere doesn't change very much. So It's a constant that comes outside the integral. Okay. So we need to count things, and in order to count anything, we need to take the help of a gentleman from Transylvania, who's called the Count von Count. He loves to count things, and he's counting bats over here. What I want to count is the dimension of the space of invariants. The space of measurements, I'll call it as M. It's a space with some dimension. The dimension can be calculated like this. The number of cross correlations are n into n minus 1 by 2. For each baseline, I have a cross correlation matrix, which is a 2 by 2 complex matrix. And for each autocorrelation, I have a single Hermitian matrix. Now, all the telescopes are measuring essentially the same autocorrelation because there's no difference between a telescope at Socorro and one in Perth in Australia, as far as the astronomical observation is concerned. So you're just measuring the same thing. So the number of autocorrelations will either be 0 if you decide to throw away your data, or it'll be 1. These are all elements of GL2C, which has got 8 real parameters, 4 complex numbers. So the dimension of the space of measurements is 8 into n minus n into n minus 1 by 2 plus 4 in A, where n A is either 0 or 1. Now, the number of invariants is the dimension of the quotient space, or the space of orbits. In other words, I have a space of measurements, and the corruptions act on the space and move one point to another point. So a point here, which I call SAB, which is the true structure of the source, could very well end up here. I've exaggerated the distance here. And you measure something over here, whereas the thing you're after is over here. These I can think of as gauge orbits, where each corruption is regarded as a gauge transformation, which is local at that telescope, at the telescope GA. I mean, this is actually the collection of all possible gauge transformations at different telescopes. So M is the space of measurements, and if I quotient it out by the corruptions, what I get is the space of invariants. If I have any function which is constant on the orbits, then I get a quantity which is incorruptible. So in the language of gauge theory, functions which are constant to the orbits are called gauge invariants. And our job is to find gauge invariant quantities, where the gauge group is given by GL2C. Now, the quantity that we call the gauge group in physics is also called the structure group by mathematicians. So if I want to work out the dimension of the space of invariants, I have to take away the dimension of the space of the number of measurements minus the space dimension of the orbit. Now, the dimension of the orbit is the dimension of the gauge group minus the dimension of the stabilizer. There might be subgroups of the group of the gauge group which do not affect the measurements. So more quantitatively, the number of invariants is dim n minus dim o, and dim o is dim g minus dim h. Now, h is the stabilizer. It consists of all those corruptions that don't really affect the measurements. There could be a corruption which, acting on the left and the right, leaves the measurement unchanged. So if you do this calculation, you'll find that this is the number of measurements, the dimension of the gauge group, 8 times n being the number of telescopes, plus 1. There is one obvious element in the stabilizer, that is, if GA is equal to some phase, e to the I theta, times the identity matrix, that will come clean through here. It will cancel out on both sides and not affect the measurements. There could be more, but generally there aren't any more than this in the stabilizer, except in some very, in one very special case of 3 telescopes, which is the smallest number you need for a closure invariant. So you find that the number of objects of invariants is 4n squared minus 12n plus 1 plus 4na for n greater than 3. You notice that the number of invariants grows rapidly with n. So when you have a lot of telescopes, like in Perth, they have a facility with 512 telescopes, though not of the Earth size, the number of invariants grows rapidly with n, and this technique becomes more and more powerful. Okay, any questions on that?
Sorry, I have a naive question. What are the invariant with respect to?
Sorry, what are the
invariant with respect to?
I couldn't hear the question. Could you speak up?
I mean, what is the invariance group under which the invariants are invariant?
Okay, the invariance group consists of GL2C to the power of n, where each GL2C acts at each telescope. That's the total product of all the corruptions at each telescope.
And another question is, how exactly are the corruption matrices shifting the points from their original location to the final location? What is the mechanism?
Yeah. So when you receive radiation at a telescope, it comes to you through some very turbulent medium. That medium introduces extra phases, which are basically corruptions by multiplication of complex numbers of modulus unity. Also, there are changes in the amplitude of the corruption. So each component that you measure is subject to these kinds of fluctuations. So the signal itself that you get, the signal that you get from the sky is extremely small. So what you measure will be some linear function, quite generally. Even if it's a nonlinear function, you can ignore the higher order terms. It'll be some linear function, complex linear function of the incoming signal. And what you measure is not quite what you should be looking at.
Okay.
Hi. How do we really know that these atmospheric interferences are like a gauge orbit? Because how do I know this actual signal doesn't have a similar feature brought about as similar to the feature brought about by the atmospheric interference?
You mean that, yeah, see, that's what the effort is, to get rid of the things which are not characteristic of a signal is the objective of this game. So even if one telescope measures some distortion, the distortion of the other telescopes will be different. So are you suggesting that the signal gives the same distortion to the source gives the same distortion to every telescope? That's
Yes, but I thought we also you were ignoring the correlations of GAs, right? We seem to be ignoring the correlations in the atmospheric interference at different telescopes by ignoring GAs.
We're cancelling them out.
Right. So okay, are you saying if the signal itself had that particular feature, then you would see it in all the telescopes or something?
Yeah. If the signal, that's right. It would be something common to all the telescopes. So that's what we're interested in. What is coming to all the telescopes? We want to get rid of what is special to each telescope.
I also have a question. How do we know that no two gauge orbits will intersect? What I mean is, why can't two different actual images of the sky give me the same distorted image?
Yeah, actually, if I think you should go back to the course I taught you last year. This is a notion of an equivalence class. Transformations.
Right. Yeah. Mathematically, it makes sense, but when I think physically, since there are distortions, I would think that two different images can be distorted to be the same. I mean, as gauge transformations, I see what's happening, but
yeah. Okay, so you're saying that. No, I don't understand the question then.
So, okay, maybe what I'm missing is...
maybe can we come back to this at the end?
Okay, sure.
Yeah. So to construct invariants, we borrow a leaf from lattice gauge theory. Think of each telescope as a vertex in a graph. There are n vertices and all possible links, that is NC2 links. Each link has a 2x2 complex matrix, CAB in GL2C. And each vertex has a GL2C, which is written as GA here, as a gauge transformation. So C goes to GCG with a dagger at the end. So what we want to do is to find gauge invariant quantities. Roughly speaking, we want to find the curl of C, the magnetic fields of this problem, where we think of the C's as being the holonomy, I mean, basically the parallel transport from one telescope to the other. We think of C's as being link variables, which is what we do in lattice gauge theory, and think of the G's as being the vertex variables. And we want to construct holonomies in standard gauge theory, just what they call Wilson loops. So I've said all this before. Assume that the G's are completely unknown. This is often not true. We do have some information about the G's, the corruption matrices, but let's assume the worst case, that we know nothing about it. We see combinations of measured correlations which are incorruptible. In a gauge theory, we would just choose a base point 0, construct holonomies of loops. Now these guys transform covariantly according to this equation. And then we would trace to produce invariants. So this whole procedure gets rid of all the G corruption information by cancelling them out. And you're going to see the cancellation shortly. This would work if the gauge group or the structure group, as the mathematicians call it, were unitary. For example, if I multiply 3 correlation matrices around a loop from 0 to A to B, and B to 0, when I do a gauge transformation, each of these terms, this term becomes these 3, this term becomes these 3, and this term becomes these 3. You can see that there are G's and G daggers sitting next to each other. And so that will cancel out all the corruptions. And finally, what I get is G naught at one side and G naught dagger on the other, but they're inverses of each other. If I take the trace of this, it'll be the same as the trace of this. So the corruption drops out. So this would work for a unitary group, but the group GL2C is not unitary. However, a slight modification of the trick works. So maybe I'll pause for questions again. This was a short section.
Yeah. sorry, sir, maybe I can rephrase my question. What I'm asking is why do we believe that distortions are an injective map? This is something I'm not understanding, because it's like noise in the atmosphere, or some signal in a wire getting tangled up. Why does this map need to be injective?
You're asking, can the G's vanish? Yeah. No, the G's can vanish, but generally, if the G's vanish, you're not really measuring both the components of the signal. You're measuring only one particular linear combination of them. So that means the experiment is defective.
I think maybe the question is why are G's linear? Because linear transformations are, of course, invertible.
Yes.
Right. But if they're non-linear in general, I think this issue will arise, right? That it may not be.
So the question is, why are these transformations linear? And that is because the astronomical signal is very small. The response of a telescope, no matter what nonlinear function it is, you can do a Taylor expansion about the zero of the signal. When this incoming signal is zero, a good experiment should measure zero output. And when there's a small amount of signal, the output of your telescope should be a linear function just by Taylor expansion, because the higher order terms can be neglected. This is related to the smallness of the astronomical signal, which astronomers take for granted, because we're looking at objects which are very far away, and the total energy incident on the telescope is a very small fraction. It's a tiny amount.
Okay, thanks.
Yeah, thanks.
And why is it GL2C and not, for instance, SL2C? Because I would have thought that the amplitude would have remained the same.
No, the amplitude also can fluctuate because there are amplifiers. There are amplifiers in the system, and they can be, fluctuating. I mean, observations in different telescopes can have different gains.
Yeah,
also even the focusing, I think they could also be focusing because of fluctuations in the refractive index and things like that, which are local to each telescope.
Okay.
Now you can get rid of this non-unitary problem by defining a hat operation on invertible matrices. Suppose I have a matrix X, which is invertible, a GL2C matrix. I can define X hat to be X dagger inverse. And that quantity is the same as X inverse dagger. Now the hat of a hat is the original matrix itself. And if I have a string of X's, which have got a hat on top of all of them, that is the same string with hats on each of them in the same order. So unlike the adjoint and the inverse, it does not reverse the order because I've done both of them. Now I fix telescope 0, I pick any telescope as a reference, and I define a string of C's, which are like holonomies that go down the closed loop. So this quantity here is a covariant. When you put in the gauge transformations, the hat has the effect of making the intermediate G's cancel out. This is a very simple thing which you can check. And this combination is a covariant, provided you start with the C and end with the C hat. And then from a covariant, you can produce an invariant by just taking the trace. And that gives you all possible invariants. Now this trick only works for even loops, those with an even number of correlations. The smallest non-trivial even loop has 4 sides. In other words, it's a quadrilateral and not a triangle. And it's not an elementary placket in some sense of the term. And this leads to a problem. We have no idea which loops are independent. And in fact, the first paper on this topic that I'm aware of, Broderick and Pescher, they are people from Perimeter who published an Aperture about 2 years ago. They treat the case of 4 telescopes, which is the simplest non-trivial case. Actually, n equal to 3 is simpler and not necessarily, well, it's the simplest non-trivial case, but n equal to 4 is pretty close to that. In some ways, n equal to 3 is harder for reasons I will explain later. And they find a set of invariants that are neither complete nor independent. Now, that's not a good thing to tell the astronomers, because they would like to know a complete and independent set. So I'll stop again for questions.
So the C's may not be invertible, right? As you said,
Yeah,
I mean,
the C's need not be invertible. That's true. That is true. And then this thing will see if let's suppose the S of the source was not invertible. That is, a particular Fourier coefficient vanished. Then that will also apply to the C's that you measure, because under linear transformation, something which is not invertible will remain not invertible. So then you will find a C which is not invertible.
so
That can
then this
happen.
construction will not work?
It will not work. Yes, right.
I see. Okay. Thank you.
Yeah, the solution to the problem of finding independent and complete objects is to reach for another object, which I call an advariant. Advariants are strings of C's of correlations with an odd number of correlations. For example, a triangular advariant can be got by just taking a base telescope 0 and constructing a triangle 0A, B0. So the three C's are 0A, C hat AB, and CB0. Now this transforms not as a similarity, but as an adjoint. So A goes to G0 A, G0 dagger. And this is what I call as an advariant. It does not transform well under gauge transformations. You don't get a G and a G inverse. You get a G and a G dagger on either side. The advantage of this guy is that it's defined on triangles as well, unlike the covariates. Now, the simplest adjoint you can think of, the simplest advariant you can think of is not the triangle advariant, but the autocorrelation. However, these guys are noisy. But let's consider the whole lot at autocorrelations as well as triangular adjoints, etc. You'll already notice when I create advariants, many of the G's have dropped out. It's only the corruption at the base telescope that remains. All the other G's in a loop have cancelled out. So this is already progress. Advariants are the building blocks for covariants. In fact, there's something like the square root of a holonomy. You're going from vector spaces to dual vector spaces. And finally, when you come back to the original vector space and form a covariant. But each of these objects, provided you put the advariants in alternation with hats on the alternate ones, you'll get a covariant. Using the advariants as the building blocks, it gives a simple solution to the problem that we posed of counting the advariants, of producing a complete and independent set. An even number of advariants alternately hatted as a covariant, and the trace is an invariant. Advariants remain advariants under Hermitian conjugation. The Hermitian and anti-Hermitian parts are also advariants. We expand them in terms of the Pauli matrices. So A plus A dagger by 2 is an advariant. A minus A dagger by 2 is also an advariant. I can take A and expand it to complex coefficients in terms of the Pauli matrices, where Pauli matrices are 1, sigma 1, sigma 2, and sigma 3. That gives me complex 4 vectors. They're not quite 4 vectors because our group is GL2C. Under gauge transformations, they transform like this. Z mu goes to determinant of G0 whole squared times an SO31 matrix. This is the Lorentz transformation. Yeah. Lambda belongs to the Lorentz group, SO31. The action of GL2C splits into 2 parts, one of which is got by just taking SL2C, and that produces the Lorentz group. And there's also a scaling by a positive number, lambda. Lambda is equal to det of G0 squared. That belongs to GL1C. The phase in GL1C is actually acting trivially. It's only the amplitude of the determinant mod squared that affects that gives you G0. So we'll first look at the Lorentz group and then come to the scaling by a positive number. So when we look at the invariants under Lorentz transformations, each advariant gives us a complex 4 vector, which is 2 real 4 vectors. So I get a string of 4 vectors from the advariants which I have found. I can form Lorentz transformations, Lorentz invariants, by taking Minkowski dot products of Lorentz 4 vectors. I can then form scaling invariants by dividing all of them by one of them. That's ratios. And that completely solves the problem that we posed. Independence and completeness are easy to establish as we work in a vector space of Minkowski 4 vectors. Each elementary triangle where all these vertices are distinct, 0, A, and B are distinct, gives us an advariant, and that gives us 2 real 4 vectors. There are n into n minus 2 over 2 elementary triangles because we left out one vertex, the base vertex. And we have n 4 vectors where m is given by this number. I get 2 from every elementary triangle and 1 from every autocorrelation because autocorrelations are Hermitian. I use 4 of the 4 vectors to form a basis and express the others in this basis. This gives us a count of 10, which are the inner products between the basis elements, and m minus 4 times 4 Lorentz invariants. These are the components of the m minus 4 vectors in the 4 basis vectors. And that works out exactly to the number we expected from dimension counting. Then we remove 1 from scaling. I mean, there's a 2 here, it should be a 1. We remove 1 for scaling to get the expected right answer. Maybe I can start again for questions.
So in what sense are they holonomies? The advariants are not holonomies, right? I mean, only when you take the
advariants are the square roots of holonomies. So if I would, I'll put it mathematically in a second. Yeah. So I'll explain the difference between the advariants and the holonomies. Okay, that will come in the conclusion, which I'm about to enter into. So the conclusion is that we have a complete solution to the problem of finding closure invariants in polarized interferometry. In the scalar case, which I didn't talk about very much, it's in the other paper, the PhysRep-D paper. We have also got some contributions about measuring autocorrelations using short baselines, which are effectively like the limit of 2 telescopes approaching each other can give you something like autocorrelations. Cross correlations go over into autocorrelations. So I didn't talk about it very much, but that's part of the results of this collaboration. The case of n equal to 3 is interesting as it does not fit the picture which I talked about. The stabilizer group is larger. That's because the number of advariants is too small to have a basis. And there are some Lorentz transformations which leave the basis, leave these 2 invariant. There are Lorentz transformations that leave these 2 invariant. That leads to 1 more invariant than we expected from the naive counting. Yeah, now coming to the spin-offs from this, one of them has to do with how we would treat non-unitary gauge groups. That involved the use of this hatting operation. Normally in particle physics, we only talk about unitary gauge groups, and there's a good reason for this. If you try to write down an action for a non-unitary gauge group, you find that when you write down the simplest action, which involves a trace, the trace actually comes from the Cartan metric on the gauge group. And for compact groups, that metric is positive definite, and you get a good action function. But in this case, in most cases, that is true. But in relativity, you actually have a non-unitary gauge group. You have SL2C, for example, as a gauge group in general relativity, which is not a unitary group. And that poses some special problems, but those problems are solved by using the hat method, which we're talking about here. So one way to think about the hat method is that at each telescope, you have a vector space. And once you have a vector space at each telescope, you also have the dual vector space at the telescope. So the advariants take you from a vector space to the dual vector space of the second telescope. Perhaps I should write this down. So suppose I have 4 telescopes here. Here there's a V and a V star, the dual space. V1 is the telescope 1, V2 and V2 star. V3.
Sam, we don't see anything actually.
Oh, I'm sorry, I'm not sharing screen. Or perhaps I'll just say it in words, that might be easier. The switching back and forth between devices can be confusing. Yeah, so I have 4 telescopes. At each telescope, I have a vector space, which is basically the E signal that you receive. And I have a dual vector space. Both of these are complex vector spaces. A holonomy takes you from V to V to V to V and back to if you have 3 telescopes, I go from VA to VB, V0 to VA to VB to V0. So that's what it does. You go from goes from one vector space to the next by parallel transport and comes back to the original one. What an invariant does, it takes you from V to V star. And if you repeat that operation, you go from V star back to V. And then if you come back to the original telescope after an even number of steps, that is a holonomy. But each link is not a holonomy. It's going from V, it's the square root of holonomy in the sense that it goes from V to V star. And after an even number of steps, you can think of it as a parallel transport along an open curve. And then when you come back to the original in a closed curve, you're forced to have at least 4 telescopes. And that's what caused the problem with using covariance in this problem. So there are some spin-offs from this. There are some improvements in, this has more to do with the first paper, the one in PhysRevD, where you understand the geometric phase better in some non-unitary contexts. And let me just say that the non-unitary context is interesting for quantum gravity because the gauge group there is definitely not unitary. And perhaps some of these methods might be useful in some problem that comes up in that context. So I think I've reached 50 minutes, which was the time which I had planned to talk for. And now we can have a longer discussion about what I said. If I understand, the talk normally lasts an hour.
Thank you. Thank you, Sam. Let's first thank Sam for a wonderful talk, and then we'll have a longer discussion as is suggested. Okay, great. So people can...
Just a minute, let me stop the share and start the share on my iPad so I can...
Sure, sure.
Yeah.
Yeah, I have one question. That suppose this pollution matrix had been singular, then it's not invertible, right?
That's right, yes.
So then this construction seems to break down. But now
Yes.
suppose that it's not quite singular, but it has a very small eigenvalue, right? In one direction it gets depleted a lot.
Yes,
Then,
that is also a case in which it will break down, because when you have noise, the small value might be wiped out by the noise and give you a singular matrix. And what is happening is that if you have an SAB, which is, let's say it is 0, a particular Fourier component vanishes entirely. And let's even talk about the scalar case. The similar question would apply there also. Then what you would measure is CAB. And there will be some complex numbers here, GA, GB dagger. And if this guy vanishes, this will also vanish. And that either might be due to the fact that the SAB is 0, or it might be due to the fact that the noise has made it 0. So you're right, we have a problem with those cases. So we will lose some invariants which we might have had if all the Fourier coefficients are non-zero.
but suppose one of them is very small,
Yes,
not
yes.
quite 0.
Yeah.
Then also one should see some problem, right? I mean, is it visible from the final formula? I mean, can you recognize that there is a problem if one of the eigenvalues have become very small?
Yeah, no, I understand. Yeah. So, so far throughout the talk, I've been ignoring other sources of noise apart from the source of noise that I'm talking about here, the G's, the corruption matrices. There are also other sources of noise, and that could take a small value and make it into 0. So my whole calculation breaks down or becomes meaningless.
I see.
And perhaps Nitya, who's my collaborator, who's in the talk, he might also have a better answer to this question.
No, I don't think so. I agree with Sam.
Okay.
It's yeah, it's a problem if they vanish. Yeah.
Okay, thank you.
I have a question.
Yes.
Have you made contact with any observational evidence? Have you kind of applied your methods to find something which has been observed or something?
Yeah, not yet. So what we have done actually is, apart from the theory, we have also done a large number of numerical tests with fake data. That is to say, we generate the data on a computer and we check that the method works and that the analytical theory agrees with the numerical data. This is not an observation yet. But I think Nitya has some other work dealing with the scalar case. And the last I heard, that was also with generated data, but perhaps he can tell us whether he's done any real observations, applied it to real observations.
Yes, at the moment, we still haven't gone to real observations, especially in the polarimetric case, because that the data that of that black hole is not public yet. So the collaboration is still working on that and they've not made it public. But what we've done is we've assumed some models for these black hole shadows and with certain polarization parameters and geometric parameters. And we kind of synthesize fake data, like Sam said. And then we've been trying to apply this to get all the information and even see, correlate what each of these invariants correspond to certain specific parameters in that model, to see if there is a one-to-one identification or if there is some combination that we can isolate for a clear correspondence. But that's ongoing work.
But I would imagine that they would have calibrated the telescopes by training them on some star before some black hole. So aren't those data also unavailable?
Yeah, as far as the polarized data is concerned, that is just unavailable. But they do provide some level of calibrated data, and these calibrations are good to some level, but we need calibrations that are precise to 1 part in 10 to the power of 5 or something like that level of precision. And just general calibration techniques do not easily get you to that level of accuracy. So that's why these sort of invariants, which are true observables and are independent of all these calibrations, have a lot of value in these observations.
Yeah, I had a question.
Yes.
So we assume that these Gs were just part of GL2C, and what if these Gs and GAs at each particular telescope, if these GAs were, if these GAs had some relation with each other, or that these GAs were taken from a subset of GL2C and not the whole, were not allowed to be any matrix in them, then will it produce more invariants or will it give us any more information?
No, let me answer the first question. You asked what are the VAs? The VAs are the corrupted version of the EAs. The EAs are the actual electric fields coming from the source. And what we measure are called VAs. That is, the relation between V and G was that VA is equal to GA times EA, where this was a 2x2 matrix. This was the 2x1 matrix, a vector. This is a 2x2 matrix. And this is a 2x1 matrix, another vector. So we would like to measure E, but we can't get our hands on it. Instead, we measure the corrupted form, which is basically a local gauge transformation applied at that telescope and produces VA.
Yeah. What I'm saying is that I'm talking about the GAs over here. So if these GAs are specific to each telescope, and they can be any matrix from GL2C. But if I was thinking of two cases, one is that either by some experimental evidences we find out that GAs can't be any of these GL2Cs; they must be a subset of them, and or these different GAs have some relation between them. Then will these two extra information give us more information in terms of invariants or something measurable?
Yes, certainly it will do that. For example, if you know that one telescope is pristine, that is not being corrupted at all. For example, if one of the telescopes is in space or something like that, then you can give more information because then you know the form of the GA, because here we have treated all the GAs as completely unknown. Any extra information that you have will only improve improve what you know. So we're talking about the worst case here where you know nothing about the corruptions. In practice, you might actually have some idea that what kind of corruptions are present at each telescope. If you fold that in, you will do a better job of understanding the source. But we're thinking mathematically, it's easier to just assume that we know nothing at all about the corruptions. And, if you, that's the worst case. If you do better than that, of course, you will learn more about the source.
Right. Okay. Thank you.
And I think Tunir had a question. No, who was it? Yeah. There was a question which I didn't quite answer during the talk. Was it Tunir or Kshitij? Okay, never mind.
Hi, Sam. Just continuing with the previous question,
Yes.
I also have something related to that. I would expect, since the electronics of all the telescopes are same and their location is also not very far from each other, these GS generally would have some correlation between them. They will not be very similar, very dissimilar. In fact, maybe they're quite close to each other. So shouldn't one expect the gauge group to be not n copies of GL2C, but rather some diagonal, or some of the GL2Cs, GL2 matrices should be the same? Shouldn't one expect that because of this physical condition?
Yeah, so let me answer that. So the context is that we are observing a tiny source, the M87 black hole. And this black hole is so small that in order to resolve this object, we need baselines which are intercontinental. That is, roughly the separation should be of the size of the Earth. And now, once you have intercontinental baselines, the telescopes are not near each other, and they could have completely different ionospheres acting on them, different times of the day, different amount of heating and all that stuff. And the electronics also need to have no correction. Even in the VLA, when you have telescopes which are in the same lake bed, the telescopes at the opposite ends of the VLA could have entirely different conditions and electronics. So,
yeah,
Nitya,
so this is what I had in mind, actually. Yeah, this is the situation I had in mind, the second one, VLA.
Yeah.
The nearby telescope,
you can expect correlations.
Yeah.
Yeah. But that breaks down when you get to intercontinental baselines, which is the kind of activity we are involved in here. And perhaps Nitya can add to this answer. It's an observational question.
Yeah, in my experience, we've always dealt with them as independent things to determine during the calibration process. And in general, they end up being independent, because the exact electronics, even though we designed them to be identical, it's not quite identical. And so we end up having different solutions. But just from a theoretical perspective, Sam, maybe this is a question I also have. Even let's just say that the two Gs are very correlated. Does it change anything about the formalism? I don't think it does, except that the dimension of the orbits may go down, or the formalism doesn't get affected, right?
Yes, Nitya, I agree. If the dimension of the orbit goes down, then the dimension of the invariant space goes up.
Yes.
Because of the difference. Yeah.
Yes.
So in that sense,
because if we have a priori knowledge that not all of them are unknown parameters, or there's lesser a number of actual unknown parameters, then there is more information to be gained.
Yes, yes. Yeah. So even in the case of identical telescopes, Nitya's answer is that some telescopes are more identical than the others.
Yeah.
Thank you.
Yeah.
I had a quick question. So the general statement is that the number of independent invariants is the number of triangles in some triangulation of your, I don't know, n-gon of n telescopes. Is that the statement?
Yeah. So what you do is let us arrange the telescopes in this fashion, putting the base telescope in the middle and all the telescopes around it in a circle. So the basic invariants that we need to look at are these triangles.
Okay.
And when you do that, you've got the whole lot, because from this you can construct any holonomy.
Okay.
And also in the scalar case, this method turns out to be better in the sense of being more scalable than the existing methods which are used in the scalar case. They have a way of working out the invariants there, but if you go from n telescopes to n+1 telescopes, the method does not scale easily. So the addition of every telescope seems to, you have to revise the whole scheme. And that our scheme in the scalar case is certainly an improvement on existing methods.
I see.
According to the Lorentz transformation properties of polarization vectors, they would, I presume, transform according to SL2C. Now you're saying that it is GL2C because of some artifact due to the amplitude amplifiers and things like that. Is that right?
No, even if you leave out the amplifiers, the focusing could cause an increase in the amplitudes, right? When some beam of light comes through, you can see that it brightens and darkens depending on the focusing properties of the light.
No,
what I'm sorry, please go on.
Yeah, so what I'm saying is, can't those be factored out? I mean, can't those be taken into account in some way, because you know what they're coming from? They are not due to
we would have to, yeah, there are methods which use, for example, in the optical astronomy, there are people who monitor the atmosphere to know what is happening. And this is called adaptive optics. They try to take that into account. But there are limitations to all these methods. And probably Nitya can give a better answer on this point than I can.
Yeah, the amplitude part, yes, comes from the ionosphere and atmospheric contribution, but also from your own electronics that you don't know a priori what it is doing. That's why the standard process of calibration exists. We know that there is a star of a known amplitude, and then compare it with the signals that we measure and figure out how much it has to be scaled in amplitude and how much it has to be corrected in phase, so that you can reconstruct that calibrating star. So even I would say that the amplitude part is also unknown. And there could, for instance, an antenna could be, for whatever reason, that day could be less sensitive and working at only 50% efficiency. And so then you need to know that it is not at its full efficiency and have to correct it by that factor.
Okay, but okay.
Yeah, one more thing I wanted to add was that if I understand correctly, so if I assume that these GAs, say for two distinct telescopes, these GAs and GB turn out to be the same. We just say that they're the same. Then essentially, as in we're forming these closed loops in which we have to come back, then we can also form open loops with these two at the ends, and they'll also produce.
You're right. You're right. Yes, that's correct. That would be effectively a closed loop because the G's are the same.
Right.
Right. Yeah.
And that will show basically that the increase in the number of invariants.
Yes, absolutely.
Sorry, but could you say a bit more about the experimental prospects of this idea? Like, for example, what do you think, like how much would it improve previous methods for specific measurements?
I'm sorry, I couldn't follow the question. Could you speak a bit louder?
Yeah, sure. Can you hear me?
Yes, I can hear you.
Yeah, I just wanted to know, like, for example, what kind of measurements and observables this method would be applied to, and then could lead to better results than previous methods. For example, I think measuring what kind of property of the M87 black holes this would be good for.
I think the question is whether these methods can be applied to give better results than existing ones. Is that correct?
Yeah, and if so, for what kind of measurements?
Yeah, well, the answer honestly is that we don't know. These methods are being used, but we don't know if the methods of, well, people are doing polarized interferometry to understand the magnetic field structure of black holes and the accretion disks. But they have already there are existing methods to try to beat all sorts of noise. This is one more, and it's probably going to compete with the other methods which are in existence. For example, so there are methods which they call self-calibration, which are very computer intensive. And those methods might also be used. But here is one more tool in the box, so to speak. If this works, then it'll be good for the observations, and it'll improve our understanding of black holes and accretion disks.
I see, thank you.
If I may add to it a little bit more, there is no, especially with this VLBI measurement of the black hole, there is no one single method that just gets the results. I think it's going to be a combination of many methods and cross checks and things like that. And this method that Sam talked about is an improvement over that aspect that recently came up a couple of years ago, and this is an improvement over that. So it should definitely yield somewhat slightly better results than what we've had from this aspect so far. But again, this alone is not going to give the full solution. And the other experimental prospects are that I, for instance, am working at low frequencies, the complete opposite side of the spectrum, still in radio. And even there are big problems with calibration in trying to understand the hydrogen structures on cosmic scales in the very early universe. And we need to have very precise calibration, which is a problem. And I've been thinking of applying some of these methods to low frequency observations as well.
Yeah, let me also mention that when we talk about cosmic scale observations, the assumption we made in this part of this, in our work, that the sky is flat, that has to be given up. You have to really allow for the curvature of the sky, and that has not been done yet.
Yes.
Okay.
So the problem that you had for the problem that you say that you will have for tallying your methods to observational data for calibration data, don't you have similar problems for the kind of simulated or simulated data that you have taken? Why don't you have the same problems there?
Yeah, see, the simulated data is just where we add the noise ourselves, no? Right? So it's more under control. We just add the kind of noise that we think will be there.
Yeah, but you can always add, say, 1 in 10 to the 5 kind of noise and see whether your method is working, as Nitya was saying. He was saying that then, since the noise is 1 in 10 to the 5, as far as I could get, that is why it's so difficult to figure out. So have you checked whether in that simulated data, if you consider 1 in 10 to the 5 noise and see whether the thing works?
I think, Nitya, this is yours.
Okay. Okay, so we use noise in a different context. So I would consider these G's as corruptions rather than noise. And the corruptions can be high. What I meant was that if you do it the standard way of calibrating the data and trying to get to the SABs from the CABs, from the process of calibration, that calibration accuracy needs to be very good in the sense that you cannot allow a reconstruction error of more than 1 part in 100,000 or so. But the calibration terms, that is the G terms themselves, could be any value, arbitrary values. And I didn't quite get the question about the problems with the calibration, whether we see that in our fake simulated data. What we do in the fake simulated data is, again, like completely randomly generate these GAs and assign them. And then we try to construct the invariants despite those corruptions. So we don't make any assumptions about the order of magnitude of these corruptions there.
No, my question is, why can't you tailor your simulated data to be exactly what you will expect in experiments.
Okay. In experiments, in terms of how much you expect the GAs to be, how much you expect what level of variations you expect in GAs? Is that what you mean?
Yeah, I mean, you said that there was some problem in applying your methods to calibrated data. I was just wondering whether whether you can tailor your simulated data and check whether the same sorts of problems arise there, or whether they can be avoided and you can apply your methods there, so that you know whether whether your methods will apply in the real case.
Yeah, no, we do try to mimic the experimental conditions as much as possible. I don't recall what exactly I said about problems with calibrated data. I said that the EHT collaboration has not released their data to be public for us to use that real data. So we have to simulate that data and work with that. But we do try to closely match what the experimental conditions are and try to simulate a data set that is similar to that.
By the way, do you know when they're going to release this data?
Only after probably they publish the paper on the polarized aspects, and they're still working on it. So I don't know.
Okay. Another question about the experiments. I don't know if you know, but like are there any planned extension of this experiment to measure other black holes? Like, is it something that is expected, or?
Yes, Sam, do you want to answer that, or should I answer that?
No, actually, I didn't catch the question. Can you repeat it for me?
Oh, yeah, sorry. I'm just wondering about the future experiments. So the EHT collaboration, for example, are they planning to do another black hole, or are they going to improve the experiments in some way? Like, what can we expect in the future?
Yeah, actually, I've heard some talk about they're wanting to look at the black hole at the center of our own galaxy. That's a little closer, it's much closer by, but also there are other problems with it, which is why they went for M87 first. I'm sure that if they can do M87, will try other nearby galaxies as well.
That's right. And with our own galaxy, the problem is, yes, it is 1,000 times closer, but it is also 1,000 times less massive. So the size of the black hole shadow is going to be correspondingly smaller. It just scales with the mass. And so that means you require a much higher resolution, which means you either have to reduce lambda a lot, or you have to, again, increase the D a lot. The other problem with our galaxy is that it also varies on timescales of days between one day and another. And so we have to capture that variability. You cannot combine all for instance, with the M87, they took data over days of maybe a couple of weeks or something like that, and they combine all that data together, because the variation is not happening on those timescales. With the Milky Way galaxy, we have to obtain that variability, which means you only get shorter integrations to work with. And so the signal to noise also gets affected. So one has to have a better instrument to be able to do that. And in terms of the experimental expansion, yes, they are planning to install many more telescopes across different continents. I think they're going to double the size of what they have now, which is about 7 telescopes across the world. I think they're going to increase that to about 14. And then the ultimate next generation plan is to also have space telescopes. And so that will give you much better resolution. And what was the other thing? Yes, and right now these observations happened at 230 gigahertz, and they're also planning at terahertz frequencies. So that will also get you some angular resolution. So these are the future plans for EHT.
I see, good. Yeah, thanks a lot.
I have an off-topic question. Is the James Webb telescope also operating under the same kinds of interferometric methods?
Actually, just 1 second. We can continue the discussion, but maybe in the interest of keeping the talk video at a reasonable length, I'll go ahead and stop the recording if that's okay. We can continue to chat.
Yeah, sure.
Yes.
Yeah, so I'll go ahead and stop the recording.